Yes, again, auditory filters are increasing bandwidth. If the noise band is less than this bandwidth of the critical bandwidth, then we are on. Then the masking noise bandwidth will when the masking noise bandwidth is increasing, the signal threshold will also increase. But if the noise bandwidth is greater than the critical bandwidth, like here, then we are constant. Then the signal threshold will be constant. We also have a different approach, notch noise. That means that there's a noise lower and upper with lower frequencies and upper frequencies. Yeah, than the tone. Mass threshold as a function of notch width. We have a notch width of 2 times delta f. Okay, and so that means we have a noise part and this Gaussian signal. The part of the noise is inside the filter. The part of the noise is inside the filter. If it is like and thus it contributes to the masking of the pure tone. So if there are a lot of noise inside the Gaussian curve, the area is big, then there's a lot of noise contribution. If there are no area, if no noise in the Gaussian under the Gaussian curve, there is no masking impact. Deviation of auditory filter. You have a power spectrum model. Assume masked threshold is proportional to the power of the noise at the filter output. Assume masked threshold is proportional to the power of the noise of the filter output. Assume that the mask threshold is proportional to the power of the noise of the filter output. Okay. The tone must have some minimum SNR within filter. We make some the test tone power at threshold. We call it PS. There's some mathematics here. Then we have it's an integral with a proportionality constant in front, and then an integral and under the integral sign is a masker power at output of auditory filter. Masker power of output of auditory filter. So the test tone power is proportional with the masker power at output of the auditory filter. Under the integral sign there is a WF, that is the auditory filter response. Auditory filter response. And NF is the power of noise masker. So if we assume that masker is white noise with power density constant in 0 and filtered by an ideal bandstop notch filter with a notch width of 2 times delta f. And so we get from the integral the test tone power threshold PS is k times n0 in front of the integral sign times an integral from 0 to f0 minus delta f, namely the masking by the lower noise band, and then plus the similar masking by upper noise band. So the test tone power at threshold is the contribution from the masking by lower pass, lower noise band plus masking by upper pass noise. So, and we have some equivalent rectangular bandwidth. The ERB equivalent rectangular bandwidth is a bandwidth of rectangular filter with same output power as auditory filter. So this drawing, this figure here is a little bit sloppy, but that means there's an integral here with the ERB times the maximum of the curve, this point here, maximum regular. The one side is ERB and the other long side is the maximum auditory filter. Yes, this area is equal to the Gaussian, this under the whole filter, bandpass filter. As ERB is bandwidth of rectangular filter with same output power as auditory filter. ERB varies with frequency. Yeah. So ERB is this 24.7 times in parentheses 4.37 times F in kilohertz plus 1. Yeah. Little bit difficult. And then we have this delta FERB. This here the page, the side here, the bandwidth times the V max is the whole integral from 0 to infinity of the auditory filter. Okay. And we also have some bars. That's a number. That's a number of as I wrote, a number of the characteristic critical bands that should cover the whole frequency area, something like that. A little bit sloppy. Frequency transformations. I'm not good in that. Level dependence of auditory filter. At medium levels, filters are roughly symmetrical on linear frequency scale. Linear frequency scale, normal first axis. Linear filter approximation holds at medium levels. At high levels, filters are highly asymmetric. So 20 dBs, they are symmetric. Mask level is a parameter, for instance, 20 dBs. Then the auditory filters are quite symmetric. If the mask level is increasing to 90 dBs, the auditory filters are asymmetric towards lower frequencies. Normal versus impaired hearing. Impaired, broader auditory filters, that means broader auditory filters, reduced frequency selectivity, and difficult to segregate sounds, speech and noise. So impaired means broader auditory filters, reduced frequency selectivity, and difficulty segregating sounds, speech and noise. And so why not noise? Because yes, you avoid so-called off frequency listening. You have to choose. Auditory system will use the auditory filter with the best signal to masker ratio, SMR. For different masker conditions, different auditory filters provide. For different masker conditions, different auditory filters provide best SMR. Yeah, you can have some noise. You have for backward noise, backward masking, and forward masking, and noise, notch noise. Using notch noise minimizes off-frequency listening effects. Okay. Putting it all together, results from masking experiments. auditory filters, excitation patterns, they are all related. Auditory filters versus excitation pattern. A sound, for instance, a kilohertz sound activates many auditory filters. Okay. Excitation pattern, the total excitation. At lower levels, filters are symmetric on a linear scale, but the excitation patterns is asymmetric. So we have here, for instance, if I have 1 kilohertz, so you have to explain this excitation pattern. You have a tone with a certain frequency, for instance, 1 kilohertz. Then you have some auditory filters, and you can see here different center frequencies and spread or broad. Yeah, the bandwidths are different. The bigger center frequency, the broader bandwidth. So you can see here this kilohertz, we have a red tone with a center frequency about 750. It intersects here, the red one, and you put and the light green one at B, and the which have maybe 800, more than 800 hertz, and then the yellow one, which has a 1 kilohertz tone, is up in C in maximum, and then we have a dark green one, this upraised 1 kilohertz tone. It intersects this auditory filter at D, and the blue one in E. So the red one, this intersection level, you have the relative excitation on the second axis. So the red one with the 700, you put this intersection, a relative excitation, the second value of the point, second value, axis value of the point. You put in situated at the center frequency of this auditory filter, the red one, and then the light blue green one is a little bit more center frequency, but below 1000 hertz. You put it upwards because it's up. The value, the second axis value is bigger, and then at 1 kilohertz you have the number C, because the masking signal and the signal for the tone is the same. So okay, and then we have the dark green one. It intersects in D. The kilohertz, 1 kilohertz upraised intersects in D, and the center frequency is 1250, and the blue one is about 1600 or 700 or something. Yeah. Yeah. But okay. Then you got this excitation pattern. You draw a curve through those intersection points centered, and you parallel translate it to the according center frequencies. Okay. At last, changes with increasing level. Auditory filters. Input of tone swept in frequency. Output at one point along basilar membrane. Auditory filters broaden on low frequency size. Excitation pattern. Input of tone fixed in frequency. Output of different points along basilar membrane. Excitation patterns broaden on the high frequency side. That was part 2. Thank you.